Hello and what's up to you all, Mindsetters, Grade 10 Mindsetters. It is a Tuesday and today we're choosing to learn physical sciences with me, of course, AB, and we have our usual lovely teacher, Tracy. Tracy, how are you?
I'm well, thanks, Abram. And how's it, Mindsetters? Hope you're doing really well and that you're studying hard.
Let me rephrase that. We have Tracy's. You guys are good, eh?
We are doing really well. Me and my little pregnant belly. But I'm doing really well.
Your jelly bean.
My jelly bean.
Right, what are we doing with you guys today?
Mindsetters. Today we're looking at electricity and electric circuits. And this is the introduction to electric circuits. We're going to be doing electric circuits over the next few weeks. Electricity and electric circuits is incredibly important. It's a section of work we do in physics, and you know, we rely on electricity so much in our daily lives, and so it's really important that you have a good understanding about it. We're going to build on electricity in grade 11 and grade 12, so it's a very important section.
Awesome, it's gotta be fun, I know that. Well, to learn more with us, Mindsetters, log on to facebook.com/learnextra, like the page, share the page, comment on the wall. I just want to know, guys, how was your day at school? How was your physics class today? How was your teacher? What did you guys learn? Any fun thing that happened today? Even the bad stuff, we want to know about all those things because we know that some of us do not always have a good day. So share with us because we are part of your family. Also follow us on Twitter @LearnExtra. Still share with us, follow us, and let your friends also follow us. But lastly, we have your notes links, which will be posted on Facebook. It's both viewing notes and the downloading link. So you have two options: to view the notes or to download the notes. And now, exciting news are you can also go to our new fresh-looking website on learn.mindset.co.za, of which we're going to show you later on. So in the meantime, you can just, Tracy is showing you guys.
I have it right on the screen right now. Mindsetters, it's a brand new website, fresh and new for you. So if you are wanting to come onto the screen, you can go and either take the tab at the top here where it says Learn Extra, and there's Learn Extra Live, Learn Extra Lessons, and some revision. Or if I go back to the home screen, there we are, Learn Extra Live at the bottom. There's a whole tab for you to go and check out Learn Extra Live, and hopefully you can go and download the notes and check everything out. It's an amazing new website design, so go check it out.
My favorite tabs are the shopping one, eh? The Mindsetters can shop. When they go to the shop, they can buy our material. Just click on it, please, Tracy.
I can.
So you guys can actually shop, because some of you have been asking, where can we get your material? We want your study packs, study notes, we want your past exam papers. We've got all of that, guys, in our shop. So you can shop for free, and we always have some sales, and yeah, it's cool because we understand that you guys are mindsetters and some of you are not working. So all our material is affordable and our resources are affordable for you guys. But last thing is we have a competition that we're running, which is probably sponsored by Casio. We're giving away these awesome, lovely calculators. We've been giving away these calculators for about, I think it's our 4th week now, so you could also be one of our winners. All you need to do is to go to the Facebook page and then check the link that says Test Yourself, answer all the Test Yourself questions, get most of them or all of them correctly, and you could be our winner for today. Last week's winner will be announced during this show. Over to you, Tracy.
Thanks so much. What we're going to be doing today, as I said, is electricity, electric circuits. So you'll see electric circuits, one, because we're going to be doing electric circuits over the next couple of weeks. It's a very, very important section, and there's lots of new stuff in here. So in this lesson, we're going to be defining electric current. And specifically, when we talk about current, we're thinking about the flow of charge. So electric current. We also will want to consider potential difference. And potential difference is something that students often are unsure about. So current, we need to define, and potential difference we need to define. And then we also want to solve problems involving electric circuits. And when I say solve problems, there are plenty of problems. There's some new equations, and we need to tackle those as well. So let me introduce you to your challenge question, because you know we always want you to get you to thinking and get you engaged in this section of work. So challenge question for you. An ammeter measures an electric current of 0.6 milliamps. 0.6 milliampere in an electric circuit, how many electrons, and remember electrons are charged particles, pass through the ammeter if the current is maintained for a period of 5 minutes. And remember, 5 minutes, that's a time value. So we've got charges, electrons, traveling for a period of time, and the current is going through. So that's your challenge question. I want you to think about it and go and try it. Go find an equation to work with. Let's get into our notes for today and summary of some notes on electricity. Now, when we speak about electricity, in comparison to electrostatics, remember when we did electrostatics, we spoke about charges, positive or negative charges that were stationary, static, that weren't moving. And so we said electrons could be transferred, but then basically there's a buildup of charge on one object. So on the ruler there's maybe a negative charge or a positive charge, on the other object the converse. So maybe on the ruler was negative, the cloth was going to be positively charged. And we looked at the triboelectric series and all of that. The idea behind those was that charges were transferred, but then they stay on that object. In comparison, when we speak about electricity, we're talking about the flow or the movement of charge. So it's again charges, positive or negative, that are moving. And the things that can be carrying an electric current would either be electrons, and that's the most common, or ions, charged particles, which could be positive or negative. So a salt water solution, for example, can allow the flow of electricity because there are charges, Na plus and Cl minus ions, that are free to move. In contrast here, we usually are speaking about electrons that are free to move. And when we say electrons are free to move, we're speaking about the charged particles. Now, when we consider direction of current flow, we often are considering conventional current. So, current is the rate of flow of charge. Every time you see the words rate, you are thinking about the fact that we are dealing with 1 divided by time. This pen is quite slow today, but we'll go with it. The current is the rate of flow of charge. So rate is 1 over time. If you think about your heart rate, you can measure, you can monitor. Your heart rate would be how many beats your heart is beating per minute. You can feel your pulse. A rate is always a measurement 1 divided by time. So the rate of flow of charge, how quickly charge is moving. What is their speed? How quickly charges are moving. That is measured in ampere. Now, Monsieur Ampere was, I think he was French, and so we name the unit after him and write the symbol with a capital letter because it's named after a person. It's important to note that in a conducting wire, there are electrons, or any charges for that matter, throughout the wire at all times, not just when the switch is turned on. So if you walk into a room and you flick on the light switch, there aren't electrons now quickly scurrying quickly to get to the light, and then the light shines. No, absolutely not. In reality, there are actually electrons or charged particles spread throughout the whole wire. Remember, what is a metallic substance made of? And if we think about metals in a conductor, you actually have the positive kernels and then those tiny valence electrons that are free to move. And they're free to move throughout the whole conductor. They're already there. They just need something to push them along. And so by providing a battery or some kind of power source, you are forcing those electrons to flow in one direction. So they're going to be moving continuously along the wire. But they're already there. So it's not that when you switch the light switch on, suddenly they've got to hurry to get into the wire. No, they already are in the wire. And when you close the switch, you close the circuit. And so there is then a complete circuit. And the power source would then force those electrons or cause those electrons to be moving. This little picture shows marbles in a tube. And I want you to consider what we're meaning by it. We've got those marbles in the tube, and it's a little animation. Now, in reality, the electrons are tiny. The positive, there's a nucleus with the core electrons around it. It's only the valence electrons that are specifically moving. So actually, the positive kernels are much bigger than the electrons. But think about it in terms of, if I pushed one marble in from the side, another marble is going to have to go out the other side. There will be continuous movement throughout that whole tube. All the marbles will move simultaneously at the same time as soon as you force the one in from the one side. In order for charge to move, it must have, number one, a complete circuit. And work must be done to push the charge along. So it must have a complete circuit, and it must have some kind of energy source. So in order to force the charges along. So something to drive the charge. A battery has potential energy that is converted into electrical energy. Think about the battery as a chemical reaction is occurring there that is producing lots of electrons at the negative terminal and a shortage of electrons at the positive terminal. So it's going to result in, from the chemical energy to electrical energy. By doing work on the charge in the circuit. Next, we need to define potential difference. Now, potential difference is the work done per unit charge. And by definition, potential difference or voltage is equal to the work done divided by the charge. EMF, or electromotive force, is the potential difference across the terminals of a battery when it's not in a complete circuit. So it's measuring just the potential difference across the battery when there is no circuit going. Okay, that's the electromotive force, or EMF. When a battery or cell is connected in a complete circuit, the potential difference across the terminals is then the potential difference. Okay, so again, it's measured with a voltmeter, before and after, okay, but it's going to, once it's in a complete circuit, it's going to be much more significant in terms of working with the battery. Now, conventional current flows always from the positive terminal of a battery through the circuit to the negative terminal. Now, that's important to note because we often consider what's actually happening. The electrons are the things that are moving. They're being forced to move from where there's an excess of electrons in the negative terminal around the circuit. But we have defined conventional current as from the positive terminal around to the negative terminal. So it's important that you put arrows on your circuit diagrams, and we'll draw one in a moment, where we show conventional current from the positive terminal around to the negative terminal. Ammeters measure current and must be connected in series. The reason for that is because ammeters have a very, very, very low resistance. And if they offer very low resistance, what's going to happen is that if you provide another path, i.e. in parallel, then current will go through that path as opposed to the path that you actually want them to go through. So ammeters always measure current, and they're connected in series. So the whole current is going to pass through. Remember, we're trying to measure the rate or the speed of flow of charge. So it's like we want a little counter to count how many are going quickly through this part of the circuit. Voltmeters measure potential difference. And you know, with difference, we want a before reading and an after reading. So they must be in parallel. Potential difference or voltage and must be connected in parallel. Voltmeters offer a high resistance, so they're not going to allow very much current to pass through them in that parallel connection. Now, I hope that's introduced these things to you, and when we come back, from the short break, what we'll do is tackle some questions and specifically draw some circuit diagrams. So, Abram, over to you.
Thank you so much, Tracy. And Mindsetters, remember, we have your notes links on the page. Make sure that you go over them. And then as we're doing what we're doing with Tracy, you can also have the notes at the same time. But also remember, the Test Yourself links is up and ready, waiting for you guys. So test yourself with those questions. We'll see you after the break. Welcome back, Mindsetters. If you just joined us now, you're a bit late, but I'm sure you can still catch up with us. We are on facebook.com/LearnExtra, and we love the questions that you guys are giving us, but I also encourage you guys to help one another on the page because that's the spirit of Mindsetters. I have a shout out from Buhle saying, I really love Mindset LearnExtra. It is helping a lot, and I love Mindset teachers. Thank you so much, Buhle Ngubeni, for that, and even other Mindsetters who are tuned in, like Tepiso saying, just tuned in, looking forward to an awesome lesson. It is going to be an awesome, already it is an awesome lesson. Back to you, Tracy.
Thank you so much. And I love hearing those comments, so thank you. Keep them coming. The idea behind that we do this is we're doing electric circuits, and we're just starting to look at building up electric circuits. So I've got an animation for you. It's a FET simulation animation, and it's a great little website. You can go and download, and you can play about building circuits and actually seeing how the electrons or the charges are moving within the circuit. So, my question for you is to draw a circuit diagram. Now, circuit diagrams are so important. You may be given a circuit diagram, or you may be asked to work with a circuit diagram if they give it to you in a question. So you need to be able to know what the symbols mean for all of the different parts, and conventional current, remember, is from the positive terminal to the negative terminal. Okay? So, we have been asked to draw a circuit diagram to indicate two cells in series. Now, in series means following after one another. So, two cells in series, an ammeter, and remember, an ammeter measures the total, measures current. Okay, so an ammeter measures current, and they want our ammeter to measure the total current, the overall current. So that's going to be helpful. We want a 2 ohm resistor in series, two 3 ohm resistors, and those must be in parallel, and then a voltmeter over the parallel connection. So I'm going to turn to our little FET simulation and see what we can do in terms of building up a circuit diagram. So if we go across to the board here, I've already started drawing it because I know these things can sometimes take a bit of time. What I've got is the batteries in series. By saying in series, we mean following one after the other. Okay, so notice the battery is connected positive, negative, positive, negative. And we've got the battery in series. Now let's have a look. Sorry. If we go across back to our screen, I just need to make sure I'm on the correct. There we are. I'm actually on a pointing device. So there we have wires, and notice the wires in the circuit have got the charges already in them. Okay, the charges are already in that circuit diagram. So I've got two cells in series. The conducting wire is connected, and do you notice I've got a battery there? Sorry, the battery's up there. I've got a resistor down here, and connected to that I've got an ammeter. Now this ammeter, let's have it across there, I want to connect to another some wire. I'm just shortening these because I want to connect two more resistors. So I'm going to pop a resistor over here, and I want these resistors to be connected in parallel to one another. Okay, So those are the two 3 ohm resistors. This piece of wire, let's get that out the way. I want some wire connecting here. And then another conducting wire. And I'm going to connect that wire over there. That's it. And connecting there. So notice as it passes through the ammeter, it's the current carrying conductor is going to split, and we've got going to have current going through both of those parts. Oh dear, did not want to do that. That's going to, let's see. Oh, there we are. Yes, we've got movement of charge. Notice here, the charges are moving, in this case, anti-clockwise. Why? Because actually it's the electrons that are moving. But conventional current would have them moving the other way around. 2 cells in series, a resistor in series, an ammeter measuring the total current, and then we've got the split. We've got 2 resistors in parallel. I'm not sure if I can split this junction. It's going to allow me to do that. It's fine. We've got there the resistors in parallel, and they're connecting up and going around there. Now there was one other thing I need to measure. One other thing I have to have on here is a voltmeter. So this is the voltmeter. And remember I said we've got to measure before and after. So there it's measuring. We're connecting over the parallel connection. Or maybe you might prefer if I've put it over there. It should also be measuring the same potential difference or the same voltage. Now, before I move away from this, I want to show you that you can also take a schematic view. Now, the schematic view is another very helpful method, because the schematic view is what you would actually be drawing if you were drawing out the circuit, and a circuit diagram. Now, I want you to notice we've got the cells in series. Those 2 cells in series, we have the current passing. Conventional current would be going anti-clockwise. So I'm going to talk that through. We've got a resistor, an ammeter, the parallel connection with 2 resistors, a voltmeter across the parallel connection, and the circuit is complete. Notice how the charges are moving, and the charges are throughout this whole connection. Okay. Let's head across to our board. Have we done everything? We did 2 cells in series, an ammeter, the measuring total current, the 2 ohm resistor, the 2 3 ohm resistors in parallel, and a voltmeter over the parallel connection. Perfect. We've done it. Let's turn to our next question. And for this question, I want to measure the current. If a current of 5 ampere is measured on the ammeter, what will the current be in each of the parallel branches of the circuit? Well, that's interesting. So if the total current that is going through this circuit diagram, if the total current is being measured at 1/2 an ampere, what will the current be in each of those branches? Well, because the resistors are the same, they're identical. You know, current would usually take the path of least resistance, but they're the same. So surely that current is going to have to split in half as well. Let's go across here. Back to our question. If a current of 0.5 amperes measured on the ammeter, what will the current be in each of the parallel branches? Assume there's negligible resistance in the battery and the conducting wires. Well, what we've got is we are measuring the current, and it should be 0.25 ampere in each branch. 0.25 ampere in each branch. The issue behind this is that current will always take the path of least resistance. Because those two are identical, we know the current's going to have to split evenly to go through those resistors. As we move on to the next question, we're going to be talking about current and charges moving. And remember, what is current? The rate of flow of charge. So, question 2. 534 million electrons pass a fixed point in a circuit in 1 millisecond. What is the current in the conductor? Well, once again, I want to always start with a list or with an equation. When I say a list, I want to know what information do I have. And what I'm going to do is just circle the information that I have or highlight it. If you've got a highlighter, always recommend that you highlight as you go along. Time is measured in milliseconds here, so that's going to be something I'm going to have to convert. And 1 millisecond is 1,000th of a second. So, time is equal to 1 divided by 1,000. I think that's enough zeros. 1, 2, 3 seconds. What is the current in the conductor? Well, the equation that I have is current is equal to charge divided by time. Now, I don't have the charge. I have how many electrons there are. So that's something I'm going to have to go and check. How do I work out the charge? Well, we've done it before. When we looked at charge, remember we identified the elementary charge is the charge on one electron. The charge is equal to the number of charged particles that you have multiplied by the charge of each one. That would make sense. The total charge is equal to however many particles, charged particles you have multiplied by the charge on each one. And this is the elementary charge, which I know is equal to 5, let's try with my finger, 3, 4, 0, 0, 0. There were a whole bunch of them. I think it was something million, wasn't it? 534 with 6 zeros. 0, 0, 0 is how many I have, and that I have to multiply by, and I've run out of space here. Let's just take that away. That I have to multiply by the charge on one electron, which is 1.6 times 10 to the negative 19 coulombs. 1.6 times 10 to the negative 19 coulombs is the charge on one proton, and so the negative would be the charge on one electron. But when I'm dealing with current, remember I said I'm dealing with positive charge, because actually conventional current is the movement of positive charge. So I'm not too worried about the negative there. Yes, I would agree there should be a negative there, but the overall, we're working with current, so it's not going to make a difference. Let's go to our calculator, and it was 1.6 times 10 to the power of button to the power of negative 19. And that I want to multiply by 5, 3, 4, 1, 2, 3 zeros, and another 1, 2, 3 zeros. So let's just check it. Perfect. Equals. That is giving me the charge. So 8.544 times 10 to the negative 11 is equal to 8.544 times 10 to the negative 11. And the unit here is the coulomb, because we're dealing with coulombs of charge. How much charge? That is going to be I'm going to be able to use very easily as I work with the equation. Current is equal to charge over time. Remember that my time was only a millisecond, a thousandth of a second. So I need to incorporate that as well. So I'm going to take my current. I'm trying to find the current, sorry. I'm going to take this charge. Let's just change pen color here. We've got I is equal to Q over T, where Q was this answer that I had previously, 8.544 times 10 to the power of negative 11. That whole thing is divided by 1 over 1,000 seconds. And going across to my calculator again, we said 1 over 1,000 seconds, so I must divide by 1 over 1,000. I'm keeping my whole answer here, and I'm going to say divided by, open brackets, 1 divided by 1,000, close brackets, equals. And that's giving me the same number, but 10 to the power of 8. So notice the same number in the front, but times 10 to the power of 8. So we aren't right to answer. 8.54, we can round off to 2 decimals, times 10 to the power of negative 8. And my unit is very different here. My unit is now no longer in coulombs, which was charge. The unit is now in ampere. So the unit in ampere, that is the current that is passing through. Now, I think that's all the questions we're going to work with just yet. When we come back, we'll tackle the challenge question, and I'm sure you're asking me lots of questions on the page, so we'll look at that after this short break.
Thank you so much, Tracy. The challenge question is posted already on our wall, so do check it out. And remember, you also have the test yourself questions to do during the break. After the break, I'll be announcing our test yourself Casio calculator winner from last week's show, so stay tuned. Welcome back, Mindsetters. Now, as promised you guys, I'll be announcing the winner from last week's Test Yourself question competition. You have a chance for today. So, guys, go to Facebook and then answer those questions. They're very simple, right, Tracy? Just challenging.
Always challenging, but I want you to be thinking. So, definitely, we want you to be challenging yourselves and trying as many questions as possible, because mindset is, that is how you apply your knowledge. It's no... of course, you've got to have the foundations, you've got to have the basics, but go and apply your knowledge. That's how you're going to learn and really improve in science.
That's why we are saying test yourself on how much you know. But well, our winner from last week's competition is Tepang Masiu. Congratulations to you, Tepang. Masiu will contact you and give you this awesome gadget that you need every day when you're about to write your exam. So all the best to you, mindsetters, who are still in need of this lovely calculator. But now, challenge question, Tracy.
Awesome. Mindsetters. So the challenge question I set for you is, an ammeter measures an electric current of 0.6 milliampere. And once again, always, I write my list, or at least highlight on the page what we've got, because you're going to be bombarded with so many questions. Also, when you write your exam paper, you turn the page and suddenly there's lots of information. I would recommend that you start your question with information. And when I say start with the information you have, I would highly recommend that you start with writing a list. Okay, so 0.6 milliampere is my current. They told me it was current, but that will help me. If I write a list, it will help me to choose which equation to work with, help me to select the right equation. And that's true now across the board in all the different sections of work we're going to do. How many electrons pass through the ammeter if the current is maintained for 5 minutes? So the question is, how many electrons? The current is maintained or kept constant for a time period of 5 minutes. So maybe on my page here, I want to write time is equal to, let's just give ourselves a bit more space. Time is equal to 5 minutes, knowing that I want to convert always to SI units. What do I mean by SI units? The standard international units that we would work with. And time, standard SI unit, would be in seconds. So I need to convert the time to seconds. So 5 minutes, well, how many seconds will that be? In every minute, there are 60 seconds. So it's going to give me 300 seconds. And we can check that on our calculator. In a moment, there it's coming. And it would be, we can clear that, 5 times 60 is going to give me 300 seconds. So notice as I go back here, what I'm doing is writing a list and helping myself convert everything that I need to convert into the correct units. Now I've spotted another conversion we need to make. 0.6 milliampere. What does milli stand for? This little m there stands for something very specific. It means that that's 0.6, that's what the number was in the front. The milli stands for 10 to the power of negative 3, or 1,000th of an ampere. So maybe you want to go and write that out and work that one out as well. I would be very happy plugging this whole thing into my calculator, but maybe if you'd want to, 0.6 times 10 to the power of negative 3 is going to give us our answer. And I want, so there it is, 6 times 10 to the negative 4, or, yeah, that's what it's going to give it to us as. So 6 times 10 to the negative 4 ampere. That still hasn't found me the number of electrons, but what do I have? I've got current and I've got time. And current and time are going to be the two ones that I will use in an equation that we used a few moments ago. Current is equal to charge divided by time. So what can I solve? Well, I can solve for the charge. I can solve for Q. So let's rearrange this equation, and I'm going to say current multiplied by time is going to give me the charge. Recognizing that the time was in the denominator, the time was dividing, so when I take it to the other side of the equal sign, I must do the opposite operation. It must be multiplying. And because I'm going to solve for Q, let's put Q on the left is equal to current times time. Current is, I worked it out earlier, 6 times 10 to the negative 4, or if you prefer, you might want to substitute the whole thing as it was, 0.6 times 10 to the negative 3, because that's what I know milli is, multiply that by the time. And remember, I said it was 5 minutes. Each minute had 60 seconds. So we can substitute those values in. Sorry, I jumped up to the top. Let's go and work that out. Well, grab our calculator. I already have that number. And I was going to multiply that by 300. And that's equal to 0.18. 0.18. Now my unit here is in coulombs, because remember I'm working with the charge. The unit in coulombs is not my final answer, but it is going to be part way there. The next part of this question is they're asking us to find how many electrons there are. So I think this, Abram, was a question on the page. How did I find the charge of an electron? Was that not kind of one of the questions?
Yes, yes.
So how do I find the charge of an electron? Well, it's the elementary charge. It's the charge on one electron and one proton. It's probably on your data sheet, but it's a useful one to get to know. Just like you might know your own phone number, you start to get to know these things. The elementary charge is the charge on one proton or one electron. Obviously, a proton is positive and an electron is negative. Is 1.6 times 10 to the power of negative 19 coulombs. So if that's the total charge, how many electrons do I have to have? Well, let's write an equation for this. Number of electrons is equal to the total charge divided by the charge on each electron. And that's going to be, well, 0.18 divided by 1.6 times 10 to the negative 19. Go back to the calculator. Happen to still have 1.8 there. Divided by 1.6 times 10 to the negative 19 is equal to 1.125 times 10 to the power of 18 is equal to 1.125. Go back, check the number. 1.125 times 10 to the negative 18, not coulombs, but rather electrons. And that is my final answer, because I've answered the question, how many electrons do we have? Abram, I think that's over to you.
Thank you. And
Thank
well
you
done
so
to all the
much.
mindsters that gave the challenge question their best, guys. I have some questions for you, Tracy, but I must say all the best to all the mindsters that are writing tomorrow. I'm seeing on the page, Buhle says she's writing tomorrow, so all the best to you. One of the questions that I have for you, Tracy, is what are the properties of a variable resistor and how does a variable resistor work? Another question is, what is the difference between a conductor and an insulator? And the last one, what is an obstacle?
Okay, an obstacle, probably you're meaning a resistor. A resistor is something that slows down charge, that slows down the movement of, or the flow of charge. And you asked about a variable resistor. Now, a variable resistor is an interesting one. A variable resistor allows us to change how much resistance is offered. So if you imagine a resistor as a piece of wire that is offering resistance or slowing down the charge flowing, then if I cause the charges to have to go through a short piece, then there's not going to be much resistance. Whereas if they have to go through a long part of that resistor, then there's going to be lots of resistance. And it's the same thing with regards to a variable resistor. We can actually set the points in terms of the entrance point and the exit point. And so we can change or vary the resistance. And then the last question you asked, Abram, was what is the difference between a conductor and an insulator? A conductor allows the movement of charge, so it allows for a current to flow, whereas a insulator, an insulator doesn't allow the movement of charge. So an insulator is going to prevent the charges from moving, and they're going to be pretty much locked in place.
All right, another one. What is the difference between potential difference and volts? That's from Mika Mutapo. And the other questions were from Liam Magyani, Balisa Makuru, and Nikelo Angel Swela, who also, by the way, said, Nikelo said, I should pass my greeting to you, Tracy.
Fabulous, thank you. So the question was?
Potential difference in volts.
Potential difference in volts. So when we speak about potential difference is the work done per unit charge. And we measure it in volts. So the focus here is potential difference is the work done per unit charge. It's also sometimes called the voltage. The potential difference we can measure, and the unit is the volt. But it's given the same symbol V, which I know can be very confusing.
Okay, on the challenge question, there's a mindsetter who made a follow-up that, was it really necessary for you to convert to MA? I think it's either the challenge question or the question
Was
before.
it very necessary? Yes, it is, because if you just plugged in 0.6, this question over here, if you just plugged in 0.6 without that, you would certainly not get the right answer. But you might have noticed that I did a conversion at the end here. I didn't use that, but I used the standard one, 0.6 times 10 to the negative 3. I always substitute in the original as much as I can, because if I've made a mistake on my calculator, which does occasionally happen, then at least I've got the original. So I hope that helps.
All right. There's a comment on the last question from Mishek Mavomo saying he got 18, not minus 18.
He got 18, not
minus 18.
Minus 18. Well, let's check. We had, where did we have minus 18? Oh, probably. You're 100% correct. Thank you for spotting that. Let's check our calculator. It was 18. You're 100% correct. Well spotted, Mishak. We need to change that and correct it here. And so that was times 10 to the power of 18. Let's see if it's allowing me to. Times 10. There we are. To the power of 18. Mishak, I'm proud of you. Well done. Well spotted. Incredibly important that you always go back and check your work, because little mistakes like that, just transferring it from the calculator, these things can happen. From Mindsetters, from me, it's signing off. Keep well, God bless, and I'll hope to see you next time. Thanks so much, Abram.
Thank you so much, Trace. Well, let me just say this, because the mindset has been writing this on the page. Said to Neymar, saying, I enjoy the show, and you're the best teacher. Please say my name. Said to, please, Abram. I just said it. Said to Neymar, thank you, and thank you for helping other mindsetters on the page. He just said it. You're the best teacher. Thank you so much, Tracy.
Thank you, Setu. You're so kind.
Thank you, and thanks to you guys for watching. We love you, and until we meet again, we love you, and in peace, we love you. Peace.